Okay, I want to talk a little bit about wave phenomenon or wave phenomena, or what we might call certain wave properties or special things that you observe about waves when you conduct experiments on them. And many of these apply to lots of different kinds of waves. Some of them only apply to certain kinds of waves. I will try to explain that here as well. There's just a lot of vocabulary here, so you're going to want to pause this video and make sure you write stuff down. If you're unclear about anything, make sure that you ask questions in class. We'll go over a lot of it. But just keep in mind that this is going to involve some memorization. And there's some terms that are very similar to one another, like rarefaction and refraction and things like that that we've seen already. So it takes a little bit of time to get used to. Okay, so let me just talk about what a wavefront is. Because we've seen different kinds of, one kind of way to represent a wave would be like this. But sometimes you'll see waves shown as wave fronts. So imagine this is your light bulb here, right? And you go, and that wave is emanated in all directions by the light bulb. We might draw what we call wave fronts, which would be like this, showing that wave going out. And these wave fronts might represent the crest of waves, right? And they're all moving very quickly because this is light. So that's a crest, and that's a crest, and that's a crest. You might have troughs as well. So a trough would be like in the middle someplace. There would be a trough here, and then also maybe a trough here. And I'm putting it on here because sometimes we see this wavefront technique used to illustrate some of the things like Doppler effect or diffraction and stuff like that. So keeping that in mind, I want to introduce very briefly at least some of the things that we're going to see. So the Doppler effect basically says that the frequency of a wave changes if it's emitted or received by a moving source. So for example, an ambulance that's driving toward you, the frequency, which is going to be the pitch of the wave, is going to change if it's moving toward you versus moving away from you. And what we see with this is maybe a car is moving to the left here, so I'm going to use an arrow to draw it, and a loud noise like the car's horn is coming off the car. So if we use this wavefront method, what you find is that the waves in front of the car are really stacked together, but behind the car they're spaced out, so you end up getting what would be like high frequency in front of the car, low frequency behind the car. And this is known as the Doppler effect. It means that in front of the car, the ambulance might sound like wee, 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 and behind the car, it's going to be like wee, wee, wee. The pitch is lower. The same is true with light, and with light it's often called red shift and blue shift. So it might be bluer in the front because that's a higher frequency, or redder in the back. So that would be the Doppler effect. Let's talk about diffraction. So diffraction, which is another thing, is when waves change their shape, they become more circular after they pass through a slit or a small opening. So example, here I'm going to do this. Imagine this wave front here has got lots of waves that are nicely spaced out, and it's moving to the right, and it comes to a slit here. When the wave front hits that slit, it changes shape and becomes circular. So that is diffraction right there. And you're going to want to put some of these pictures into your illustrations. So two D words that are easy to mix up but have totally different results. Sometimes you will have something that involves two-slit diffraction. So hopefully you've drawn this. But a two-slit diffraction might look like this. You've got an opening, boom, boom, and the light hits this and creates two rounded things. And this causes what is known as interference, which is when two waves overlap. So that's not the only way to cause interference. You could cause interference if you've got a wave traveling here and you have another wave traveling in the opposite direction. When they pass together, at some point it's causing interference, and we'll have a separate video on what interference looks like. So two waves overlapping is interference. Might want to pause it if you haven't written stuff down. I'm going to erase this and continue with a couple other things. Okay. So the next term I want to introduce is polarization. And polarization gets at the fact that light has a certain kind of orientation or way in which it vibrates. Polarization. And this is for light waves only. And imagine this. We have a wave traveling in that direction. It has a certain frequency. It has a certain wavelength, etc., etc. Now you could have another light wave that was exactly the same frequency and the exact same wavelength, but instead of being vibrating up and down like that, was vibrating sideways in and out of the board, and its vibrations would still be perpendicular to the direction of motion. It would look a little bit like, trying to imagine. I mean, that's not a good picture. But I mean, it's supposed to have the same frequency and wavelength and orient. But basically, imagine like the plane of vibration is tilted differently. And that's what polarization gets at, is that you can restrict, using a polarizer, you can limit certain orientations of light from getting through. So you can limit only light of a certain, I'll just use your word orientation, to get through. And this works, example, for certain kinds of sunglasses. It helps reduce glare because you're eliminating some kinds of light. It actually helps get more light in the right orientation as well. So light that might be not tilted like that, but tilted just a little bit off, will actually get corrected to the same orientation, whereas light like this, orienting back and forth, even if it's going the same direction with the same frequency, is not going to make it through the polarizer. And that is for light only. So that's one example for polarization. Another term I want to introduce is resonance. And resonance is basically vibrations within an object caused by standing waves. That build in intensity. An example of this is when you see opera singers singing and shattering a glass. Like you break a wine glass. And that's caused by this term called resonance. So you're basically bombarding objects with its natural frequency because the wave matches the natural frequency of the object. So all objects want to resonate at certain natural frequencies, and if you can bombard it with waves of that same frequency, you can get what's called resonance, and you can cause things to oscillate to the point where it might even break, like the singer with the wine glass. So that is another term that you're going to need to know, and we're going to go over in more detail at some point. Let me talk about last thing I want to talk about. Let's talk about lasers a little bit. Laser is when you excite electrons and you emit light, and that light has certain properties. But the light is called what is monochromatic, which means it's all the same color. So as we will see, you can have red light that is made up of many different colors of light, but monochromatic light is made up of all of exactly the same color of red. It is called coherent light, meaning it's all traveling in the same direction. And they do that by putting a little slit on the laser so that no light escapes if it's going in the wrong direction. This is why the laser beam is so kind of tight and closely together. Now, you might ask yourself, does that mean that a laser light has to be polarized? And the answer is no, not necessarily. Sometimes laser light can be polarized, sometimes it may not be. But keep in mind that polarized light, well, you can have light going to the right, like this, that's the same color and the same frequency, which would make it monochromatic, but it could all be traveling to the right, which would make it coherent, but some of it might be vibrating up and down, some of it might be vibrating in and out, or at various angles. And if those vibrations are still perpendicular to the motion of the object, like in and out of the board is also perpendicular to the right, just like up and down, you could have light that is not polarized that comes out of a laser. So polarization and lasers are not necessarily associated, although you could make a polarized laser. Lots of terminology here, and I think that about does it for this particular video. I'm going to let you write anything down, and thank you very much for watching.